All right, well, we're doing good. We only have two more people left, so we're not terribly behind. So we'll just move ahead.
Press on. All right. Next is Nate, who will be introduced by Hunter Canadian. I don't know if I said it right.
It's close enough. Thank you. Yeah, hi. My name is Hunter Kuniainen. I'm a aerospace engineer at the Space Sciences Lab at UC Berkeley. I've had the pleasure of working with Nate Hontz over this summer, who is getting ready to start his undergraduate degree in engineering. So Nate has been very dedicated to his work this summer. I've taken meetings with him while he's been both on a boat and in the cabin up in the mountains. So no matter where he's at, he's putting in a lot of fantastic work. So without further ado, I'd like to pass this over to Nate.
Nate, are you sharing your slides yourself? Great.
Yes. So for my summer internship, I worked on the Foxy 5 sounding rocket, and I worked on making a mount for a X-ray generator that is to be used to align the rocket's sensors and optics. The Focusing Optics X-ray Solar Imager Foxy rocket is a sounding rocket that is designed to observe and study the sun in the X-ray wavelength of light. The focusing optics on the rocket have to be precisely aligned with the corresponding X-ray detectors before the rocket is launched, and for that, the Foxy team uses a portable X-ray generator. This X-ray generator needs to be mounted in a way that allows for easy alignment, and that requires a custom mounting system. This is the mounting system that we designed for the X-ray generator. The assembly is intended to allow for mounting the X-ray generator in a variety of used for precise alignment of the X-ray optics. The optics must be aligned right before launch as they are sensitive and they may be misaligned during transport or vibration testing. The initial requirement for the mount was that it had to counteract the X-ray generator's 27-degree aperture angle, so the aperture could be pointed directly at the Foxy optics. The initial design of the mount was based on a wedge with a 27-degree angle from horizontal. A sliding and rotating mechanism was then added to the design so that the position of the X-ray generator's aperture could be adjusted. The next version included a mechanism for vertical rotation of the X-ray generator, and this was so that misalignment of the payload with the sun could be mimicked during alignment, and that allows for just a better alignment. Lastly, the mechanism for vertical rotation was added, and I just made everything, and I just added other stuff that was needed in the design. So the X-ray generator mount is in three ways. The X-ray generator's position on the mount can be changed up and down, be rotated around the central axis, and the X-ray generator can be rotated vertically around its aperture. For the sliding adjustment, the X-ray generator can be moved vertically up to 0.4 inches from the center line. Sliding the X-ray generator all the way forward will align it with the central X-ray axis for precise alignment, and represents 1/8 of an inch of vertical movement. The entire assembly can also be rotated around the central axis, and it includes screws that can be tightened to lock in any position. The generator can also be rotated vertically around the aperture. Each alignment mark on the. My final deliverable for the project was an interface control document. This included a mechanical drawing, a bill of materials, a series of assembly instructions, and the user instructions needed to effectively use the device. This is the station drawing, which is a basic mechanical drawing of the device. This is a bill of materials, which is a list of all of the components needed to construct the device. These are the assembly instructions, which show how the device is meant to be assembled. And this, and this are the usage instructions for adjusting all of the different things on the device. In completing this project, I gained a sense of how engineering projects are realized from a broad concept to completed design, and this includes detailed mechanical drawings and a bill of materials, and I also learned how to use the CAD software Onshape to aid in the design process. I'd like to thank my mentor Hunter Kaniainen. I would like to thank Dr. Lynn Kaminsky. I would like to thank Dr. Eliana Arista, and I would like to thank NASA and the entire N3 team, and I would like to thank Sonoma State University.
Thank you, Nate.
All right. Well, you're very welcome, Nate, because that project looked like a whole bunch of fun. Did you actually then build it or just do the design?
I don't think it's been built yet.
Right. Well, great that you got to learn all that software.
Quite a head start on your future engineering career too. This is really great. I love hardware projects. They're so hard to do virtually though. So kudos to you for being able to do that.
All right. So if we don't have any more questions, I'm gonna make sure that Tim gets his time. And look, we're practically on schedule.